Well, hello, chemistry students. This is Mr. Kinney. I'd like you to get this entry in your calendar updated for my substitute teacher on the .cam. If you could push the enter button now and give the students about a minute to get their homework written down. We will be doing notes in just a moment on nuclear radiation. Your homework is to finish the conversions worksheet that I gave you last week. That is the half sheet that looked like this, and you need to work on the back side. I asked you last week to do the front, and so you need to work on these problems on the back. So I'll get those collected. We'll go over them on Wednesday. This right here says text worksheet, those pages right there. Let me zoom out a little bit now. Wrong way. Sorry. So what I'm going to do is in class today after the notes, you're going to have this paper to be practicing writing some of the nuclear equations, some of the breakdowns of the nuclear equations. So this is going to be classwork, but your homework is going to be for you to use your textbook and get these questions answered. So this is on the back. So this is where it's the old worksheet, page 268, and you'll get this page too, and that'll get us. Sorry, pretty zoomed in here. So anyway, this will be your homework tonight, getting this completed and getting the conversions worksheet completed. I've got stacks of these up front. If you missed one, lost one, you can get them. All right, well, let's get started with nuclear chemistry, or at least nuclear reactions. Again, for my substitute teacher, at any point, if I ask you to pause, push the enter button on the .cam, and that'll pause this momentarily. Well, this is nuclear reactions. And this will be in chapter 25 of our textbook, and that's where you'll be working tonight in your homework, and I believe it starts on page 798. Some nice diagrams there to look at, and then we'll be doing some reading from it as well. So, first off, Roman numeral 1, I'm going to put here for nuclear radioactivity. It's just going to define radioactivity as the process of giving off rays. Wow. Okay, so we got radio. Then we have activity. And again, that's the process of giving off rays. And we'll talk a little bit about what that is, but the let me zoom in a little bit more. I'll have to make sure I don't write too small here for you all to see. Process of giving off rays. And I guess we really need to also to define what radiation is. We tend to hear that a lot, and I mean, right now you've got radiation filtering down on you. It's from the light bulbs and the lights above, the sun sending out radiation, the photons. So we're constantly bombarded by radiation. Your cell phone is irradiating your pocket right now, or your hand if you're sneaking around texting when we're working on the notes. So radiation is particles or rays from a radioactive source that can penetrate objects. So, and again for my sub, if the students feel like they need it, you can pause this momentarily so they can get these down. Particles or rays, that's important. It could be particles. Rays, by rays what we're meaning is energy forms, okay? It could be photons of light, it could be microwave radiation, it could be the sound waves coming at us right now. Let's see, so particles or rays from a radioactive source. And again, from a radioactive source, that would be something that gives off these rays. Okay, the radioactive source, and oh, sorry, but I think I put it, that should be a C right there. And that can penetrate objects. Well, okay, some of them can. You have different types of rays. Some are high energy, some are low energy. Okay, so sub, if you need to pause for just a moment, you can do so, but then I'm going to go on right here. Now we need to go back to the beginning part of the class back in September when we talked about isotopes. Yeah, we're going to be going back to isotopes. You need to remember that isotopes are those elements of an atom that just have extra neutrons or even fewer neutrons. Isotope notation. And a lot of what happens is with radioactive elements is that they are so big, they have so many particles, they just cannot hold on to all of the particles. And they begin to drop some. And that's the process of radioactive decay. You might have heard that term. So, isotope notation. And let's put our friend, good old friend carbon right over here. So there's the symbol for carbon. Darken that in just to make it look a little bit easier to see. And with isotope notation, we'll put the atomic mass up at the top. Excuse me, I misspoke. That's going to be the mass number, okay? Because that was one of our terms. The mass number is this on the top. And remind you again that the mass number is the protons plus neutrons. So it's the protons in the nucleus plus the neutrons. It's very specific. It's not the average atomic weight that we see on the periodic table. It's specific for whatever particular isotope we're talking about. In this case, this would be carbon-12. And down below, we'll always put the atomic number. No, almost always the atomic number. And a reminder for you that the atomic number tells you which one of these, is it protons or neutrons? Yeah, it's the number of protons. By definition, that's what the atomic number tells you. Now, a way that this could be written, this is the carbon-12 isotope. It could be written like this. So if you see carbon-12, that's telling you it's the isotope of carbon that has a mass of 12. There's also carbon-14. Okay, this is a radioactive isotope that is common all around us, and it has a couple extra neutrons compared to the most common form of carbon. And when these neutrons break away, we can measure that, and that's how we can tell how old past remains are. When they find, an old woolly mammoth or something like that, they can measure how much carbon-14 is left in the remains, and they can compare it because we know how much there would have been when the thing was alive. Anyway, let's get going. So now we're going to do the types of radioactivity. So this will be part A. So this was up here, this was all just kind of some introductory stuff. So the first type is going to be alpha decay. Alpha particle decay. Now we first heard about this when we talked about Mr. Rutherford doing the gold foil experiment. He shot alpha particles. And in parentheses, we'll kind of make a fancy looking A. Okay, that's supposed to be a kind of real stylized A. So this would be an alpha emission. So when an element breaks down, giving off an alpha particle, we say it's alpha decay or it's giving off an alpha emission. And basically, here's the definition for that. And after I write this out, then if you need to pause, we can do that. It's an atom that loses a helium nucleus in the process of decay. So an atom that loses a helium, I'm just going to put HE for helium, nucleus. Now it's just the nucleus. It's not the electrons out there. So I'm going to write this, then if you need to pause for a moment, we can. So when we write that out, since it's helium, we put HE. Oh, sorry about that, everybody. I went off the page. I didn't mean to do that. It loses a helium nucleus. So we're going to write HE, and helium has the most common isotope has a mass of 4. There's 2 protons and 2 neutrons. And then, since it has 2 protons, it's going to have this written like that. So, let's do an example. If you need to pause for a moment, go ahead, but we're going to get going here right now. Let's take the element uranium 238. It's on the periodic table near the bottom left side, down in the rare earth metals. It has 92 protons. And when it goes through alpha decay, now when you're doing this process, we'll say alpha decay. Sorry, I don't make a very good stylized A. on that. I'm really bad at that. I don't know if I can find a nice diagram in here for you that shows it. Well, I can't find it in the book, and I don't want to take time to hunt it down. Oh, okay. Well, here. Okay, just so you're used to seeing it there. Oh, where am I? Over here. Oh, man. Sorry. Just not with it this morning. So you can see from this how it's just they use it as just it's a kind of just a stylized A. All right. Okay, so back to our problem here. So now we're going to have uranium undergo an alpha decay. Now what that means is it's going to lose a helium. So it's going to go ahead and kick off a helium. So I'm going to go ahead, let's first write that out. So it changes from uranium into helium. Now what happens is, with an alpha decay, since we have lost a helium nucleus, we've lost 4 particles from the nucleus. So when we go to rewrite this, we have uranium-238 over here. We need to do 238 minus those 4. So 238 minus 4. Okay, go ahead. You can do the math. Come on, do the math. That's right. So it's going to be 234. So the new particle that's formed here is going to have a mass of 234, and it's going to lose 2 protons. So for 92 minus 2, it's going to have a new atomic number of 90. And when we look on our periodic table, my nice colorful one. No, of course it's hidden away. So now what we do is the element that has an atomic number of 90 is going to be the element thorium, because we lost 2 protons. That takes us over here to the element thorium. So now we know that when uranium-238 isotope goes through an alpha decay, it's going to form a helium nucleus, and it's going to get a thorium nucleus. And you can always, when you add these 2 sets of numbers here, these will always add up to that, and then these 2 numbers will always add up to there. Okay, so when we do a decay, that's how that works. All right. Now the next type of decay is it's beta decay. So beta decay. Alpha particles are big, easy to find, so this is one of the first particles they were able to find for radioactive materials. I'm using them out slightly. Okay. So for beta decay, and when we do this, you kind of make a stylized capital B. And so if they say, you have a reaction occurs and it emits a beta particle. Now, here's what happens is, with beta decay, you have a neutron. It's a little different than what happened over here. You have a neutron, and it gets converted, it changes into a proton. Now remember, neutrons are neutral. Protons have a positive charge. So what happens is, when this neutron gets converted, transmuted into a proton, it also kicks off an electron. So, there we go, let that bell stop. So we got this positive charge and this negative charge equal to a neutral charge. So let's write one out with carbon-14, which I'd mentioned earlier. So let's put over here that we have carbon-14. So we'll put carbon. 14 means it has 14 particles in its nucleus, and since it's carbon, every carbon isotope, no matter what it is going to have 6 protons. So I'll put a reminder for you. Well, you can see that this is the atomic number, that's the mass number. So what happens is, since we're having one of these neutrons convert into a proton over here, okay, so we're not going to have a change in mass. The mass is going to be the same on this one because a proton has the same mass of a neutron. So we're going to still have the same mass number, all right? But since one of the neutrons has changed into a proton, this number of protons is going to increase by 1. So now it's going to become, the new atomic number becomes 7. And when we look on our periodic table to see what element has an atomic number of 7, it's our friend nitrogen right up here. So we can put the symbol for this. And then we're going to put plus. We need to put the electron. Now there's a way that they'll show the electron. So we'll put electron, and we'll put that its mass is 0. And since it doesn't have number of protons, it just has a charge, we'll just put a -1 just to say, hey, it's got a negative charge, just to let us know. So there's no proton there. In fact, you want to think of it, it's got the opposite, of a proton. It's got a negative charge there. So there's an example of a beta decay. It is when an element has one of its neutrons change into a proton. And so it changes into a different element. And in this case, when we add these up, 14 plus 0 equals 14. Okay, 7 minus 1 equals 6. So those numbers still kind of add up when we go across. And then the last notes for today. Okay, I know you're really bummed out. No, you're not bummed out. Is gamma radiation. Now, gamma radiation is very high energy. In fact, if I could get a gamma ray flashlight and shine it at you right now, we'd all be dead because gamma rays have incredible energy. And this is kind of what we tend to think of when we think of the bad effects of radiation. Okay, and gamma, the symbol for gamma, it kind of looks like a cute little Y, sort of, okay? So, let's kind of get you an example. It's the Greek letter gamma, so it looks like this right down there, okay? So kind of a little stuff. There's the gamma ray. Now, what's going to happen here is that usually when there's a gamma radiation, when gamma particles produce, it's usually an association, with something else, okay? And so we're going to get an example of an alpha decay with where you're getting some gamma ray particle here. So we're going to start with our friend thorium, the isotope of thorium, TH. So we got thorium, and this is thorium-230. So it has 230 particles in its nucleus, okay? That's a lot of stuff to try to hold on to. Since it is thorium, it has an atomic number of 90. And it's going to go through, we'll put here that it's going through a beta decay, excuse me, my mistake, sorry, a gamma decay. And also in this case, very often this is associated with something else. So we're going to have a little alpha decay as well. So first off, since we're going to break this down, alpha decay. Coming back over here. When we have alpha decay, we get a helium nucleus formed. Okay? Not a helium atom. There's no electrons associated here. Helium nucleus. So we're going to come back over to here. So we might as well, let's go ahead. Let's put our friend helium on. I just recommend put helium first, since we know that it's an alpha decay. And helium has a mass number of 4 and its atomic number 2 on the periodic table. Now, we got to take a look at thorium here, because now thorium gave up 4 of its electrons to make this helium. So let's see, 230 mass number minus these 4. Can you work that out for me? Come on, work it out. And yes, it's going to be 226. So the new is mass number for this, whatever is formed, is 226. And now it's lost 2 of its protons. So thorium has lost 2 of its protons. So it's no longer thorium. It has changed into a new element. And see, 90 minus 2. Uh-oh, is that, I think that's 88, isn't it? 88. So let's look on the periodic table to see what element has 88 on there. And let's see. Oh, there we go. Okay, we started right here, and it backed up. So you go over 2, it becomes radon over here. A lot of times radon gas is in the water table, and sometimes they have to do radon detectors in different people's houses to see if they're getting too much radon. I remember back in the late 1990s at our schools, we had to all do these radon tests to make sure we weren't getting too much radioactive isotopes coming up through the ground. Anyway, we're not quite done here yet, because we said, so we've got our alpha particle that formed here, but also we have a gamma particle, and a gamma ray is also emitted, which is just energy. So we'll just say plus, we'll just put the little stylized Y, plus the Y, that's the gamma ray. Again, this is an energy particle. So with a gamma ray, it itself is not going to reduce the atomic number. It's a little bit of the mass of these reactants get converted into energy. Remember the great equation E equals mc squared? Well, a little tiny part of the mass over here in the process of these reactions, a little bit of the mass gets converted into energy, and that's in the form of a gamma ray. So with that, I think I'm going to stop these notes. Your job for the rest of the period is to first, in class, I need you and your partners to work on these questions. The substitute will hand these out to you. And it's just like we've done before. We've got an alpha decay, and I'll help you set up a couple of these right now. So an alpha decay is going to occur. So when you get this set up right away, we know a helium nucleus is going to be formed over here. And you can go ahead and get, I think PA, if I remember, it's protactinium. Cool name. Okay, plus, then you're going to have to subtract the 4 from the atomic mass, and you're going to have to subtract 2 from here to figure that out. Now with this one, the second one, okay, now it's a beta decay. And when you look at your notes, beta decay means, all right, you're going to have an electron kicked out to begin with. Okay, an electron that has 0 mass, but it does have a -1 charge. Okay, now since beta decay, you're starting with francium 87 over here. Excuse me, francium 223. My mistake, I misspoke there. So we know that since there was no weight, no mass change, the new element is still going to be 223. Okay, but now since you've gained a proton, you need to add that increased atomic number here. So for the rest of these, it's just practicing doing this. And just like in our notes, when you're doing an alpha decay, just make sure when you're done, when you add up these mass numbers, it should equal what you started with. When you add up these protons down here, the atomic numbers, it should equal what you started with. For the beta decay, the same thing. You're going to get an electron kicked out here. You're going to have the atomic number increase by 1. I mean, that's really, in fact, you know what? On these notes right here, beta decay, you can put a note. Atomic number increases by 1. Okay, I mean, that's what you look for when we're doing the test on this. If we got the atomic number is increasing by 1, it's a beta decay. If over here, if the new element, if it's, I would say if it's mass, this is for over here, if mass number decreases by 4, then you have an alpha emission. Okay, again, I'm not styling up, that's supposed to be a fancy looking A. You have an alpha emission, you have alpha decay. Okay, so and a gamma, the gamma ray itself is not going to change anything, but it's usually kicked out in the process sometimes with the really big elements here. So get to work on practicing those, and then tonight your homework, finish the back page of this. This is in your textbook. This is like a worksheet from your textbook, and then finish working these problems over here. So there, goodbye. Signing off.